What's up, guys? We're going to continue finding zeros and talking about the multiplicity of those zeros with polynomial functions today. And we're going to be looking at standard form. We have already looked at factored form. So standard form is when you have terms separated by addition and subtraction, and those exponents are written from the largest to the smallest in descending order. So when I'm looking for the degree here, I'm looking for the largest exponent within that function, which is 4. So this is degree 4. It has a positive leading coefficient. So our end behavior is on the left, y goes up, and on the right, y also goes up. So these have the same end behavior. Now, in order to find the zeros for this function in standard form, we're going to have to factor this. So I already went ahead and I factored out a GCF. So if I take out an x from x to the 4th, I'm left with x to the 3rd. If I take out an x from x to the 3rd, I'm left with x squared. And if I take an x out of minus 4x squared, I have negative 4x left over. And then if I take that x out of that last term, all that's left is a negative 4. So we have to continue factoring what's left inside of those parentheses if we can. So I'm going to write this off to the side, and because we have 4 terms, I'm going to try to factor by grouping. And just so I don't make a mess, I'm going to come off here to the side. So I'll group these 2 at a time. I'll put a plus sign right in the middle of those 2 groups, and I'll factor out a GCF from both groups. So I'm going to factor out an x squared and then a negative 4. After you factor out a GCF, those groups that are left inside of those parentheses should be exactly the same. That is one of your factors, and then whatever's left, so the x squared minus 4 here, is the other factor. So I'm going to go ahead and write those 2 factors right underneath that first step so that I can go ahead and see if I can continue to factor, which I can because that x squared minus 4 is a difference of squares. So I'm going to factor that x squared minus 4 into x plus 2 times x minus 2, and then I'll keep the rest of the factors that are already in there. Now that I have all sets of factors, I can't factor anymore. I'm going to go ahead and set each one of those factors equal to 0. So we have to set these factors equal to 0 to find the zeros. So that first one is already done for us. The second one will give us negative 2. The third one will give us positive 2, and the last one will give us negative 1. You're just solving one-step equations there. Now, because I know the end behaviors here are both pointing up, I can plot all 4 of those x-intercepts. They all have multiplicity 1, which is an odd multiplicity. So that means that they pass through the graph. So now I should be able to use that information from the end behavior and the zeros to connect those points all together to make that sketch of the graph. So I'll start on the left side. I want this to pass through negative 2, pass through negative 1, pass through 0, and then pass through positive 2, which will give us this like W shape. Remember that you can check the shape of this graph in your graphing calculator. So we'll look at another example. This one is also degree 4, and it also has a positive leading coefficient. Those are the only 2 pieces of information that you need to describe the end behavior. So we know that this goes up on the left and up on the right because it is a degree 4, an even degree with a positive leading coefficient. So now we just have to find the zeros. So we're going to have to factor this x to the 4th minus 16. Now, x to the 4th minus 16 is a difference of squares. So x squared times itself gives us x to the 4th. 4 times itself gives us 16. So this can be factored as a difference of squares, x squared minus 4 and x squared plus 4. So I'm writing x squared plus 4 in the front because we can't factor that anymore, but we do have x squared minus 4, which is another difference of squares, which factors into x plus 2 times x minus 2. And now that I have all of those factored, I'm going to set each factor equal to 0. So this first factor is going to end up giving us two imaginary solutions. So it's kind of a wasted factor. It doesn't give us any zeros because it gives us imaginary answers. But we will get two x-intercepts here. When we solve x plus 2 equals 0, we get x equals negative 2, and x minus 2 equals 0, we'll get x equals positive 2. So we'll be able to still sketch the graph with the knowledge of those zeros and the end behaviors. So I'm going to go ahead and plot those two x-intercepts on this sketch of that graph at negative 2 and positive 2. We know that the end behavior goes up on the left and up on the right. Each one of those x-intercepts has multiplicity 1, so they're going to pass through those x-intercepts. And again, we can check those in our calculator. It just looks like a very skinny, tall parabola. Okay, so here's one for you to try. Find the degree and the leading coefficient to help you describe the end behavior. And then I want you to try to factor this function and then set the factors equal to 0 to find the x-intercepts. Pause the video here, try out all those things, and come back when you're finished. Okay, so we can see that this is degree 3 because the biggest exponent we see is a 3. The leading coefficient is also positive, so this is going to go down on the left and up on the right. All that you can factor here is a GCF. So you can take out an x squared from both of these, and you'd be left with x squared times 2x minus 3, which you would set both equal to 0. If you take the square root of both sides for that x squared equals 0, you're going to get x is equal to 0, but with multiplicity 2, because that's an x squared. This tells us that it's just going to touch or kiss the graph at x equals 0. Over here on the right side, we can add 3 to both sides. We'll get 2x equals 3. And then we can divide by 2, which will give us x equals 3/2, or we could say that that's just 1.5. That decimal will help us graph a little bit better. That x equals 1.5 has multiplicity 1. So that tells us that this point just passes through the x-axis based on our notes about multiplicity and whether we have even or odd multiplicities. So I've got enough information now to be able to sketch my graph. I'll put the point at 0 here, and then I'll put a point in between 1 and 2 at 1.5. I know that this goes down on the left, so I'll put my arrows there, down on the left side and then up on the right side. I know that the picture of this is just going to kiss the graph at x equals 0, and it's going to bounce right off just like a trampoline, and then it's going to pass through that 1.5. So our graph kind of looks like this weird looking N. So unfortunately, not all polynomials factor in a way that we know how to factor. For this example, we can see that this is degree 3 with a negative leading coefficient, so it's going to go up on the left and down on the right. But if we try to factor this by grouping, we see that the things that are inside of those factors are not the same. So this does not factor. So we're going to have to learn different methods of finding zeros. That'll have to do with the rational root theorem, the remainder theorem, synthetic, and long division. So if you do not know how to do long division by hand with regular numbers, you're probably going to want to look that up before we move forward. So at this point, if you get to a polynomial that does not factor, we can't do anything more until we learn all of these other theorems and this long division. So thanks for coming. We'll see you next time when we talk about rational root theorem, remainder theorem, synthetic, and long division. Have a great break.